A robot video goes viral because the motion looks human. The harder question is, what had to work in the real world for that 10-second clip to happen at all? Today we unpack the mechanical story behind the demo, specifically why manufacturers claim high torque density and how a three-stage planetary actuator achieves legged locomotion without being the size of a small car. When you look at a humanoid robot walking, it is easy to assume the complexity lies in the software controlling its balance or the neural networks interpreting sensor data. However, the physical foundation that makes this movement possible is hidden inside every joint, the actuator. The central engineering challenge here is torque density and backlash control. If we cannot pack massive force into a compact volume while maintaining zero play between gears, the robot collapses under its own weight or fails to execute precise steps. The common assumption among curious viewers is that adding more gear stages simply multiplies strength linearly without penalty. This intuition leads many to believe a single-stage gearbox should suffice if we just make it bigger. But in robotics, space and mass are not infinite resources. A one-stage planetary design creates an immediate physical bottleneck for legged locomotion. To achieve the necessary torque output with a single reduction stage, the gears must be physically massive. This increases the moment of inertia at the joint, making the limbs sluggish and heavy. The robot would struggle to accelerate or decelerate quickly enough to maintain dynamic balance during walking. Furthermore, one-stage designs often cannot meet the strict backlash requirements needed for precise foot placement. Backlash is the tiny amount of play between meshing gear teeth that allows them to move freely without binding. In a robotic leg, even fractions of a degree of slack can translate into centimeters of error at the foot. This lack of stiffness causes instability when the robot pushes off the ground or lands from a step. The control system constantly fights this mechanical slop, consuming energy and risking falls before any software algorithm is ever called upon to intervene. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This brings us to the two-stage solution, which many consider the industrial standard for high-performance robotics. A two-stage planetary gearbox offers significantly better torque multiplication than a single stage while keeping the overall package size manageable. The first stage reduces speed and increases torque slightly, passing that force through an intermediate shaft to a second reduction stage where the final output is achieved. This configuration effectively doubles the gear ratio compared to a one-stage unit within a similar envelope. However, even two stages hit a wall when we demand extreme performance for legged locomotion in compact humanoid frames. As engineers push toward higher torque density and lower backlash simultaneously, a purely mechanical trade-off emerges between size, weight, and precision. The intermediate shafts required to bridge the first and second stages add length and mass that can become problematic in tightly packed joint designs found on modern humanoids. Additionally, achieving ultra-low backlash with only two reduction points requires extremely tight manufacturing tolerances that drive costs up exponentially while still leaving a margin of error for dynamic loading events like running or jumping. To solve this paradox, we turn to the three-stage planetary actuator. This design is not merely an incremental improvement. It represents a fundamental shift in how mechanical advantage is distributed across the joint. By introducing a third reduction stage, engineers can achieve gear ratios that are unattainable with one or two stages without inflating the physical footprint of the unit. The torque density increases because each individual stage handles less load than it would alone, allowing for smaller, lighter gears to be used in aggregate while still delivering the massive output force required at the joint. The critical insight here is how this architecture manages backlash. In a three-stage system, the total reduction ratio allows the final output gear to move with extreme precision relative to the input motor. The cumulative effect of multiple reduction stages dampens any play that might exist in earlier gears. This means that when the robot's foot contacts the ground, there is virtually no mechanical slack for the impact energy to absorb before transmission begins. The result is a joint that feels stiff and responsive, allowing the control system to maintain balance with minimal latency or correction lag. This engineering reality explains why manufacturers claim high torque density only applies to these complex multi-stage designs. A one-stage unit simply cannot pack enough force into the required volume without becoming unwieldy. A two-stage unit gets close but often sacrifices either size constraints or precision limits when pushed to the extremes of dynamic locomotion. The three-stage planetary actuator is the mechanical solution that satisfies all competing requirements. It fits inside a human-scale limb, delivers the torque needed for rapid acceleration and deceleration, and eliminates the backlash that causes instability during complex movements. Without this specific architectural choice, legged robots would either be too heavy to move efficiently or too imprecise to walk reliably on uneven terrain. The software can compensate for some mechanical limitations, but it cannot overcome the fundamental physics of a joint that is too loose or too massive. The three-stage design provides the physical intelligence required before any code ever runs. It ensures that when the robot decides to take a step, its body actually has the structural integrity and responsiveness to execute that decision in the real world without collapsing under the load. This teardown reveals that the secret to humanoid locomotion is not just in the algorithms or the sensors, but in the precise mechanical architecture of the joints themselves. The three-stage planetary gearbox stands as the only viable path forward for achieving the necessary balance between power, size, and precision required for machines that can truly move like humans through a complex physical environment. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.